Hello. I'm going to do an example of the solution to a system of ODEs where the eigenvalues of the 2 by 2 matrix A are repeated. In fact, in this example, the eigenvalues are 0 and 0, but we'll get to that. So how do you solve these things? We've talked about eigenvalues of a 2 by 2 matrix. The eigenvalues are solutions to a quadratic equation in lambda, the eigenvalue. So the eigenvalues are either real and distinct, or repeated and real, or complex conjugate pair, a pair of complex conjugates. So we've dealt with the distinct real, the complex conjugate pair, and now we have the repeated real. And actually, in a way, this is the easiest of them all, especially if you follow me and you don't follow the book. Okay. So this problem can get kind of complicated, and if you read your textbook or Paul's notes, you might think it's kind of complicated. But I'm going to give you this fact that makes it really simple. All right. So let's hear. Suppose A is a 2 by 2 real matrix with eigenvalues lambda 1 equals lambda 2. Then the solution to the initial value problem, the x dt, is that matrix A times x, with x of 0 is an arbitrary initial condition, x naught, is here. Its x of t is x naught plus v naught times t, all times e to the lambda 1t, where v naught, and that's like a velocity, v naught is computed as a minus lambda 1I times x naught. Okay, so let's just head straight into it. Problem 6 is an example of this. They don't have problem 6, they don't have the arrows, so I'm going to add them because I prefer the arrows to show that you have vectors. Okay. So dx dt is this matrix A times x, and the initial condition is given. All right. So, so step 1 is compute eigenvalues. So the determinant of A minus lambda I is the determinant of 2 minus lambda, -4, 1, -2, minus lambda. So it's that times that minus that times that. 2 minus lambda times -2 minus lambda, all minus -4, so that's a +4, is 0. All right, so we got this quadratic equation is a plus lambda squared, and then I have a minus 2 lambda plus 2 lambda, they cancel. -4 plus 4 equals 0. In other words, lambda squared equals 0. So the eigenvalues are lambda 1 equals lambda 2 is 0. All right. So this case, so we have here, let's summarize this. Lambda 1 equals lambda 2 is 0. So step 2, okay, since lambda 1 equals lambda 2, we're going to compute this v, okay, is equal to a minus lambda 1 I times x naught. And that's actually v naught, okay? And then here we have the a, and lambda is 0, but let's not forget that this thing here is x naught. The lambda 1 is 0, and x naught is 2, 3. The initial position. So that means that v naught is just the matrix A, 2, negative 4, 1, negative 2, times 2, 3. Okay, well, this takes a little bit of work here. I'd like to do the multiplication and take care of the signs in my head and then leave the addition and subtraction for later. 2 times 2 is 4. And then I'm going to add minus 12. Right? And then I have 1 times 2, that's 2, minus 6. That's minus 8, minus 4. Okay. By the way, just note that minus 8 minus 4 is an eigenvector. Two, 3 isn't an eigenvector, but minus 8 and minus 4 is. All right, but, all right. So we've computed, so now we have everything we need. Use that formula. This one here. All right, the solution is going to be x of t is equal to x naught, 2, 3, plus v naught t, negative 8, negative 4, times t. That whole thing gets multiplied by e to the 0 t. Right? All right. So let's get rid of some of that. Let's just summarize. We have that as x naught. And we've computed that v naught is negative 8, negative 4. And we can get rid of this. Okay. So what do we have here? Let's write this. The e to the 0 t is 1. This is going to be 2 minus 8t and 3 minus 4t. All right. So we're pretty much done. The web work problem wants us to write this solution as x1 is 2 minus 8t, and x2 is 3 minus 4t. Okay. So, good. So I want to show some pictures of this now, but before I show the pictures, I just wanted to mention a little bit about why we call it V naught, right? This solution is like a particle moving in the plane with initial position 2, 3, and a constant velocity of minus 8, minus 4, okay? So in the case when the eigenvalues are repeated as 0, the solution just is motion in the x plane, x vector plane, with constant velocity. And we'll do another example later when I have to modify that by the scale factor or the scalar multiple that either grows if lambda 1 is positive or decays if lambda 1 is negative. All right, and now let's show some pictures of this. Okay, here we're going to share the screen. All right. Okay. Actually, let's make a little bit more room by not showing the bookmark bar. Okay. So here's our familiar website. Let me first show the repeated eigenvalue 0, 0. This is the vector field that we are talking about. A is 2, negative 4, 1, negative 2, right? 2, negative 4, 1, negative 2. And there is an eigenvector, and it's the to one direction is an eigenvector. 2 to the right and 1 up is an eigenvector. Any multiple of it, like for instance, -8, -4 is an eigenvector. But there's only one eigenvector that's linearly independent, only one eigenvector here. So that's why it's not like the previous case. Okay, with two different distinct eigenvalues. So let's look at these solutions now. I think it's down here. We'll go to the slope field applet. In our usual way of doing this, we'll convert it to a system with x and y. And dx dt is 2x minus 4y. And dy dt is x minus 2y. These are the scalar x and y. All right, and then the initial condition is 3, 1. Right? So, okay. No, it isn't. It's 2, 3. Okay, that's more like it. So I started at point 2, 3 at t equals 0. And as time goes on, I move in the v direction, -8, -4. I go 8 to the left and 4 down every second. In fact, in 1 second, I'm off this page. Okay, and if I click anywhere else in the page, I also just move along a straight line in this plane because I'm moving with a constant velocity. And if I'm below the axis here, my velocity vector is up and to the right. If I'm above here, my velocity vector is to the left and down. And there's a bunch of places here where I don't know if I can get them. There are some places where the velocity vector is 0. It's like if I start here at, say, 2 plus 1, and I submit that, I don't know if you can see it, I'll clear all curves. I submit that, I don't see anything. If I start with 2, 1, and I compute 2, 1 is an eigenvector. So if I start with x of 0 is 2, 1, my solution would be x of t is 2, 1 for all t, because the velocity is exactly 0, so I just stay put. So that's a special thing with these. If the eigenvalues are 0, 0, there's a lot of solutions that are constant solutions. Everywhere along this eigenvector line, let's show here, everywhere along this blue line, cyan line, is an equilibrium point. X prime equals ax, and the solution starting on this line is x of t is a constant. Okay, it's things like 1/2, things like 1/2, 1/4, things like 0, 0. All of the points, initial conditions on this blue line give me equilibrium solutions where x of t is a constant function. All right, so we'll do another example in a while where we have non-zero eigenvalues. Okay, bye.